Hello and welcome to our webinar, Next Generation Technologies and Materials for Advanced Mobility Applications. My name is Lisa Arrigo, your moderator, and I'm with SAE International, the host for this 60-minute program. Today's webinar will examine challenges that automotive manufacturers are facing as the industry is being transformed, challenges in thermal management, power efficiency, and friction and weight reduction, among others. And then we'll discuss the role material technology is playing in that transformation. Our speakers are from Freudenberg Sealing Technologies. They are Michael Blake, an application specialist overseeing e-mobility and automotive sales who has both Six Sigma and Lean Systems green belts. Joseph Walker, the Global Technology Director for Materials and Laboratories, who holds more than 20 patents in the fields of materials applications and compositional chemistries. And Ray Sparagowski, the Technical Director of Automotive and High Performance Plastics in the company's Global Fluid Power Division, who has a Lean Systems black belt. In the second half of today's program, our speakers will answer questions from the audience. So, if you have questions, please send them at any time by using the Ask a Question box on the screen. And now, let's welcome our first speaker, Application Specialist Mike Blake.
Hello, everyone, and welcome to our webinar here. And thank you, Lisa, for the introduction. As you guys heard from Lisa, my name is Michael Blake. I'm the application specialist here, and I focus on e-mobility relative to the automotive segment. And without further ado, let's get started. So Freudenberg is a 169-year-old family-owned company that services 32 different market segments, from automotive to aerospace, energy to mining, construction, food and beverage, among many others. And to meet the expectations of our customers in each of these industries, Freudenberg has some core competencies. The first being product-specific research and development units. So this is for product families like gaskets or radial shaft seals, and each of these R&D units is in contact with the respective engineering departments. Our second core competency is our philosophy that our customers are our strategic development partners. So we bring design proposals from experts in their field rather than a build-to-print product. As well, this allows us to carry across innovations from one industry to the next, since we are the experts in each of those industries. Our third core competency is we own our own tools we own our own tool expertise and our tool shops. So this allows faster product development as well as assuring production quality. And here we also have a global standardization of production equipment. So whether that part is made in North America, China, or Europe, we're using the same product and manufacturing methods to produce that product. Here at Freudenberg, we are the inventors of the radial shaft seal, and it's known as the simmering throughout Europe. And we've worked with our customers for decades, perfecting technologies that help our customers address the most challenging issues with the internal combustion engine, whether that's weight reduction, fuel and friction reduction, aggressive media, aggressive oils, or high temperatures and speeds. We've been able to meet those market needs. And as the industry goes through transformational change to alternative powertrains, we are seeing some of those same challenges in this market. But this change is also driving considerably new needs for materials and products that can address these new technical issues. So I want to briefly talk about the market and how our company is addressing the shift away from the internal combustion engine. So here we have a prediction of powertrain mix between fuel cell, battery electric vehicle, hybrid, and internal combustion engines. And this is going up to 2035. Although no one knows the future, we can see the trend of e-mobility is already happening and gaining momentum. And here at Freudenberg, we see three different forces that are driving these changes, and those are governmental regulations, new players in the automotive market with lots of funding behind them, as well as a societal change. And in the transition to electric vehicles, we see at Freudenberg two key applications that are disappearing for us, and those are engine and transmission. As you can see from the product portfolio here, there's a variety of seals, a variety of products that we make that will no longer be around if there's no battery, if there's no internal combustion engine. And with those applications going away, we see a significant erosion in our sales. And in our worst case estimations, you'll see on the left here a complete internal combustion engine vehicle market going to a battery electric vehicle market. We could potentially lose 70% of our sales if we did nothing to meet those market needs. Fortunately, at Freudenberg, with a 169-year history of successfully reinventing itself, we are doing that again to meet these new market needs. And with our new products and innovations that Freudenberg has used existing technologies to come up with, we have developed a product portfolio that is focusing on two specific segments within battery electric vehicles, and that is the battery and the thermal management systems, as well as electric motors and e-powertrains. Here is some of the variety of the different products we make, and I'm going to dive into a little bit more depth into two specific products, one for each battery and e-powertrain, that address the customer's needs going through this transformational change. One challenge our customers have been faced with is learning to deal with large lithium-ion battery housings. So there's two main functions that are required of pressure regulation for these large housings. And those are, with any sealed housing, you would need a breathable element, so something to allow air to go in and out to regulate the pressure during normal temperature increases and decreases, and a secondary function that is only required for lithium-ion batteries, where when a lithium-ion battery cell decides to vent, it releases a large volume of very hot gas very quickly. And so this, in terms of the housing design, requires an overpressure release function, where you can release this large volume of gas and maintain low pressure within the battery housing. As you can see pictured here on the top, we have an example of a pressure graph of an unregulated pressure housing, and this would be in the blue line, you have the normal pressure cycles of the daily increase and decrease in temperature. The pressure inside that housing would increase and decrease with a sealed housing. And then in the event of a lithium-ion cell venting, you would see a large volume of gas be released very quickly, causing a very high pressure spike in that system. And this could potentially cause damage or worse items on that pressure housing. And you can see here on the bottom, this is a pressure-controlled housing, where during the normal cycles of breathing and or the normal temperature cycles of the day, you can see small pressure differences in the housing. And then in the event of a lithium-ion cell venting, you would see a small pressure increase, but a not overall pressure gain, preventing that damage from the housing. And here you can see is the way we accomplish this pressure regulation at Freudenberg is a technology we call the diavent. And here is a picture of a cross-section of the diavent, where we have those two functions of normal breathing and overpressure release accomplished within the same unit. And that first function of breathing, you can see, is accomplished by this pressure regulating section. And this is a breathable nonwoven membrane that allows gas to go in and out of the housing to regulate that pressure for your normal daily cycle of a lithium-ion battery. This also will not allow any dirt, debris, or water to get into the housing. As well, the secondary function is accomplished by a silicone umbrella valve, pictured here in orange, that will open up and allow a large volume of gas to be released very quickly. And then, since it is an umbrella valve and made of elastomer, it will come back down and seal, and after that large volume of gas has been released, it will come back and seal and maintain that seal. And this unit here is rated to IP 6K, 9K, so that way we can maintain the integrity of that battery housing with this unit. And another challenge, a new challenge that our customers have been faced with in the electric vehicle industry, is known as electrical bearing erosion. And this is where a rotating shaft, most commonly an input shaft, becomes electrically charged from excess electric potential floating around within a housing. And this electrical charge can discharge between the shaft and another metal component. And when this electricity discharges, it can sometimes carry metal with it and remove metal material from those surfaces. And so what can happen is, in a bearing, it will take away metal surfaces in that bearing, causing that bearing to remove metal and erode away, as well as this can potentially happen within gears or other moving components within the system. And this could also potentially cause premature wear or failure. So what we've done at Freudenberg is developed a technology to help meet this request from our customers, and that is what we call the electrically conductive radial shaft seal, or an e-nonwoven. So what we've done is we developed a nonwoven material that is based out of carbon fiber and is electrically conductive. And you can see pictured here on the right, we have a traditional radial shaft seal with a nonwoven excluding device that actually is electrically conductive. So this nonwoven is making that electrical connection between the shaft, that dynamic shaft, and the static housing. So this allows, when that excess electric potential is built up within that unit, it allows a safe discharge of that electric potential along this path to prevent any other damage to any other components within the unit. So we've actually developed 3 different generations of this technology, varying in electrical resistance from the shaft to the housing from 1,000 ohms to less than 1 ohm. And we do this by varying the material of that carbon fiber nonwoven in our design. And we've even found that our generation 3, that we estimate around less than or around 1 ohm of resistance from the shaft to the housing, it has even been beneficial to our customers for insulating electromagnetic interference from leaking out of a housing between the rotating shaft and the housing, where your traditional radial shaft seal is located. So I've reviewed for you 2 technologies that we've created to address our customers' needs in this changing industry. And with all of our technologies and innovations here at Freudenberg, we believe our foundation is in-depth materials science. So now I'd like to pass the presentation over to Joe Walker to speak more about materials.
Thank you, Mike. Good day, everyone, and thank you for participating in this webinar. And again, thanks to SAE for hosting it. I'll be discussing just some of the challenges and drivers shaping advanced material developments specific to the new e-mobility requirements. The effect of alternative powered vehicles on the overall automotive market continues to evolve. This percentage impact seems to change every magazine publication cycle, but regardless of the actual percentages, the impact of alternative powered vehicles will, without doubt, have a significant impact on our traditional vehicle markets. At Freudenberg, we see an increased focus on fuel cells and battery technologies, which really dominate the current emerging power landscape. These changing propulsion technologies drive changes in material technologies that also has to advance at as rapid a rate as possible to address these heretofore unknown demands. There are many needs for advanced materials during the evolution of this new automobility marketplace. A few of these opportunities are presented here. Let's look at some of the key opportunities. So first, we see the battery. We see that sealing the battery elements and thermal shielding and thermal management are all opportunities. Next is the need for SORT materials. These materials not only provide a traditional sealing function, but also all communication between the seal and the vehicle controllers, not to mention the whole Internet of Things relationship and metadata that can be obtained from the vehicle. I'll discuss this in a bit more detail in following slides. The motors themselves present some demands for new materials as well. One such demand is for the elimination of electrical interference, which is important for sensors and also the entertainment system. And Mike just talked about that with some of the e-nonwovens that we've got. So another one that I'll address in more detail later in the presentation. The charging system shows opportunities for advanced materials as well. The use of rubber and plastic composites to integrate assemblies more efficiently and provide improved sealing function is certainly an opportunity. Longevity is yet another ever increasing demand, whether it's in traditional sealing functions or also corrosion resistance. So new seal materials designed to resist the electrolytes or to reduce or eliminate permeation of hydrogen is another opportunity. And once again, we see that thermal management appears along with EMI and RFI shielding as an added function. In the driveline area, the challenges are for lower friction seals, lower stiffness boots, etc., all to minimize the power demands during function to basically improve the overall efficiency. So thermal management is clearly a reoccurring theme, and I'll address this shortly. In general, advancements in battery electric vehicles, fuel cell vehicles, plug-in hybrid vehicles, all of these are driving new material developments. So first, let's discuss some of these smart materials. So smart materials are materials that have augmented functions. So they not only seal, but they sense changes in their environment, and then they respond in a very predictable and reversible and controllable manner. Some examples of these smart materials and their functions are shown here. So you have magnetic elastomers, you have electrically conductive elastomers, you have dielectric elastomers, and then you have special thermal management systems, which could be phase change or fire resistance or extreme temperatures or what have you. So if we, as an example, look at one of these smart materials, a material that more or less gets intelligence from magnetism. In this case, we've developed a special magnetic filler. We designed this and incorporated it into the rubber and imparted some special magnetic properties. This is different than just adding conventional ferrite or something like this. This is truly unique. So by making use of these magnetic properties, now smart rubber materials enable activation of things such as sequencing valves, which are some of those are shown here. Signals such as frequency of activation and sealing force can now be extracted and utilized by the vehicle controller systems. Another smart material enables the vehicle to detect wear, in this case, rotating shaft sealing element. In this application, the elastomer is a composite construction where part is an electrically insulating elastomer and the other one is an electrically conductive elastomer. The materials technology here lies in both forming the composite structure and in the development of the electrically conductive material. In yet another example of smart materials, here I'm showing another example using the advanced dual material alloy composite for detecting and communication of sealing deterioration. In this application, we have the principles discussed previously on rotating seals being applied to a reciprocating seal. The electromagnetic spectrum relative to automobiles spans anywhere from 500 megahertz to, or for wireless communication, to 2.4 to 500 gigahertz for Wi-Fi. You know, of course, that many vehicles are really rolling hotspots. And then it extends to 2.4 to almost 2.5 gigahertz for Bluetooth connections. And then all the way from 0.7 to 2.7 for 4G LTE wireless callers, coming in at 5 gigahertz or 6 gigahertz. So the EM spectrum is limited and must be maintained to allow reliable communications. In North America, of course, we have the AM frequencies, which are unique to our world, and the reliability of these communications requires that the interference must be protected against so as to maintain the reliability that we depend on. So again, smart material technologies have been designed to address this risk. Here are two further examples of smart materials based upon conductive sealing elements. In the first example, on the left, shows the traditional approach of using a conventional rubber seal, which is shown there in red, as an environmental seal, while a metal mesh, shown in silver there, is used as the EMI RFI shield itself. With the advent of new conductive technologies, we are able to eliminate the need for a dual material seal and instead consolidate function with a single material where the new materials technologies are made use of. In this example, a high-performance material exhibiting both chemical and thermal resistance can be used. Most generally, lower-performing elastomers were offered, which meant decreased lifetime in service. In addition, the number of sealing elements are reduced and can now be considered for automotive assembly operations. Next, we see an electrically conductive fluorocarbon rubber there as a rotating shaft seal. Note that this was an in situ bonded element to a steel case. It's possible that the material can bond to a full plastic case as well. This kind of technology can also address the electrical bearing erosion and certainly the interference that can be done within the infotainment system. So thermal management has been talked about quite a bit in our drivers, and it's increasing in safety importance as well. So in the following slides, I discuss some application, but due to time constraints, I've only picked the ones that are of the most critical importance. So clearly thermal management of batteries is needed, and especially with lithium-ion batteries getting some unfavorable attention today. Freudenberg is developing thermal management technology to address safety concerns, and as well as other battery technologies by design of novel fire-resistant materials and extreme temperature sealing materials. We've designed these special flame retardant chemistries meeting very stringent regulatory requirements to address occupant safety. Here is one such example of a flame retardant material that originally was developed for aerospace engine applications. Freudenberg is in a unique position to leverage and really harvest its material technology from its other markets to shorten the time to market for addressing new automotive needs. This is an example of that. This material is a composite rubber alloy with a conventional silicone rubber interfaced with a layer of an elastomeric intumescent material. Shown here is a series of pictures that show the response of this rubber composite alloy. In the upper left, you see about a 1500 degree flame being applied to the intumescent material. The top of the intumescent material, which, by the way, this thickness is only 2 millimeters here. The top of the intumescent layer was 1,000 degrees cooler than the bottom where the flame was, just in 2 millimeters of thickness. So shown in the middle is a conventional UL94 so-called flame retardant material that had the same exposure to the flame, and it had burned completely through. The photo on the right shows the side that intumesced. This is the side that was directly exposed to the flame, and the lower picture is the top of that 2 millimeter test sheet. Clearly, there was a substantial protection there. The new technology affords substantial protection from raw flames in safety-critical application with no toxic substances being liberated. And this new material can be fabricated by conventional molding techniques as well as by extrusion, which is shown here. So the diversity of fabrication methods allows for a wide window of design opportunities. With underhood temperatures as well as higher shaft speeds being driven by today's new engines, Freudenberg again takes the cue from our other markets with the design of extreme temperature seals. These are seals that are expected to continuously operate at temperatures exceeding 205 degrees C. Here are results of some extreme temperature testing. These fluorocarbon-based compounds offer exceptional chemical resistance as well as sealability. You can see here compression sets that have been done on O-rings. O-rings were chosen because it's the most severe. After exposure to 250 C, almost 500 degrees Fahrenheit. The values are less than 30 for the special low-temperature polymer. In addition, one can see in the upper right chart that the retained properties are very good even after 1,000 hours at 250 C, which is defined by SAE J2236 as the continuous upper temperature limit for elastomeric members. The flexibility and hardness is measurably good. So these materials would be expected to operate continuously at very high temperatures. So at this point, I've discussed some of the advanced materials that I felt would be of significant interest to you. My specialty has been with the rubber materials, so now I'd like to introduce Ray Sparagowski, who will continue the discussion on our new high-performance thermoplastic materials. Ray?
Thank you, Joe. I appreciate that. My name is Ray Sparagowski. I'll be talking today about high-performance plastic materials. These are injection moldable or compression moldable materials. My concentration will be in the areas of friction reduction, wear reduction, and weight reduction, the use of the materials to do these things, and moving these materials to extreme operating conditions, which allows you to move them in applications where they traditionally would not be used in the past. If you look, one of the key benefits we need to do to use these materials and get the benefit from them is to understand the effects of wear. Freudenberg has developed their own wear standard for doing so. The main reason for doing this is to eliminate noise and variation when we add fillers to the systems to really understand the key failure modes of these systems. That way we can know what the impact is of a filler and how that will affect the failures. There are two key testing conditions that we want to look at, of course, is dry. What do we have when we do not have lubrication, and then lubricated or wet wear. The standard that we developed, the primary importance is to control temperature. The data I'm going to show you today will be temperatures at 150 degrees Celsius. That's our standard that we normally would test to. This test method uses a disc of material with 6 grooves. This is to eliminate debris from getting into the test condition to further reduce the noise and variation so we can understand what the materials are doing. The counter surface is a metal counter surface. That can be different hardnesses and different materials. Typically, we'll use a D2 steel at a Rockwell hardness of 23. That is a ring-shaped member that goes against that disc. It is important to note that surface finish is particularly controlled in these tests. We do not use a radial or lathe type record player finish. We use a linear finish. This is intentional because we want this to be an aggressive test. We want the material to have to go with and cross the grain with every revolution. That's to be more aggressive to get better understanding of wear conditions. The finish we hold varies depending on the method we're testing for. So when we do dry testing, we're going to be using a surface finish of RA of 0.4, a smoother finish. When we move to the lubricated conditions, we actually become more aggressive. We want to be a more aggressive test because we have lubrication present. We move to an RZ of 7 standard. We do a number of different tests depending on material criteria. You can see those in the points in red and the points in blue on the graph. Those graph depicts a PV value, a pressure and velocity value. So as you move up in pressure and velocity, you become more aggressive. Our standards in the data we'll talk to primarily today will be C2 dry and C5 wet. These are the conditions we would normally evaluate materials for. What you're seeing now is a graph of some of the test results we've gotten. The top graph is wear. This is a wear factor for measuring how much wear occurred. There are 2 conditions here, the dry condition in the lighter color, and then the more darker color would be the lubricated condition at C2 versus C5. The materials, the orange, the red, and the blue material are some common materials used today in the industry for high-performance plastics, a PEEK, a Torlon, and a Vespel grade. The last 2 materials are PEEK grades used by Freudenberg. There are Quantix grades. The green one has been traditionally used by us for many years for seal rings and other applications. And the gray one is a new material that we've recently developed. The bottom graph shows friction, and you can see the dry friction is typically much higher in these type of materials than the lubricated condition, where the lubrication becomes much lower friction and you don't see as much variation. One of the critical things you'll notice on this graph is the effect of controlling friction is critical for us. So this newly developed material we mentioned, this Quantix 5514, it actually has an extremely low dry coefficient of friction, and it is equivalent to the lubricated friction. And that also has much lower wear. Traditionally, the dry friction hasn't been as critical of a concern because the applications were fairly high in lubrication, but we're seeing more and more movement as we move into e-mobility and other areas where they want less lubrication or lower viscosity fluids, and dry friction becomes a critical factor. So we're really moving to a point now where we need materials that are slippery when dry, and that's going to be critical for how these materials can move to higher applications and not have failures. Taking the information we just had, the same materials we just looked at, which were tested at this condition C5, which happens to be a PSI times feet per minute PV value of 400,000, you can see that the materials have very little variation in wear. The wear is on a logarithmic scale, so there's huge changes as wear as you move up this graph. But when we move to condition C6, you can see now we went from 400,000 to 800,000 PSI times feet per minute. At that condition, we cannot pass the 4-hour test with the Torlon, where the other materials still continue to be used. If I again move to doubling that to the C7 condition, this is a 1.6 million PV value. We see the Vespel materials will not pass a 4-hour test, and you can see the example of the Freudenberg materials. They're both doing very well. We accomplish this by clearly understanding how the failure modes occur. By knowing what the fillers can do, we can develop these materials to have extremely high condition and operating performance. On the next slide, we are looking at the effects of using the same technology in a PTFE material. PTFE is commonly used for dry applications. It has low friction, but it does not like high loads and rough surfaces. So traditionally, if we would conduct a lubricated test with the RZF7 test, you can see the results we would get on a material. In yellow, you see our example of quantum 19-1. That wear rate is in the tens of thousands. It's very, very high because PTFE cannot handle that rough surface. It will destroy the PTFE material very quickly. But using this technology, we recently developed this quantum 19-8 material shown in purple in the middle of the graph. This material actually performs wear at a level of these traditionally injection moldable thermoplastics like Vespel, Torlon, and PEEK. So you can now see an extremely high roughness resistant PTFE that is able to be used in applications where it traditionally wouldn't in the past. So we are taking advantage of this for new applications where we may want to replace metal spacers or other items for use in PTFE along with our other thermoplastic materials. Here's a case study we did where we actually took a part that's being made in production today and tested it to validate our wear performance methods could be measured. In this case, we're looking at a pinion gear application. The part in production has a couple of grooves in this washer that's used between these pinion gears, and it's made out of the Vespel SP21. This material is a very high temperature material, used often in very low lubrication conditions. We ran that on our test stand, and you can see we got a wear rate that was quite large, 0.11. That material actually wore away and would not pass the 4-hour test condition that the test was designed for. And you can see in the picture, no grooves are left from the wear. We made a developmental material using some of these filled systems, and this Quantix 72-4 material was tested. It passed the 4-hour test with almost 1/10 the wear, virtually no wear, because of the technology we used to improve its durability. So another example of how actual part testing can show and validate this improvement in performance. Weight reduction is still very important too. So as we start to take and look at parts and where we may have not traditionally considered using metal, plastic material in a metal application, we may be able to do so as we move to these more extreme materials that can handle wear and keep friction reduction. But they also allow us to take weight out of the system. So I've got 3 examples here to show you how the weight can be managed and you can take advantage of this technology. The first was traditionally an aluminum part. It was a piston used in an accumulator transmission. We moved it to a plastic material, PPS, a high temperature material. We reduced the weight by 75% and lowered the cost for the entire assembly. So it was a win-win using the technology. The middle item is a spacer that was tested and designed originally in aluminum. The customer had issues with the aluminum wearing out. This particular part has some splines that engage a spline on the ID, and they were having fretting of the aluminum and issues with the spline fit after running and testing. We launched a polyamide or Torlon material, and we're able to solve the problem with Torlon where aluminum would have failed. So another example of how these plastics can be used in metal replacement. The final one is an example of a validation test that we passed full validation on. It's a bearing replacement. It's used in a torque converter. I'll note that this doesn't mean we can replace every bearing that's out there. In this particular application, we were highly lubricated, and we had relatively low loads. The original part was a metal roller bearing, as you can see in the picture there. We designed a new part using some of our specialty material, and we're able to validate that the test could pass. This was used on the 6R140. It did reduce weight by 80% and offered some significant cost savings. So another example of how changing what is used today, if you understand the failure modes and look at the application, you can remove metal and put it in plastics. You can lower friction and potentially save costs too at the same time. So these examples really rely on a lot of the material technology, but I'm going to now move to how do we use material technology in combination with design to make these go even further. So in the next examples, we're going to talk about two products that we have that are designed to lower friction and to reduce the energy usage. Levitorg is a low torque thrust washer designs that we use. These allow us to take fluid pressure and fluid film to generate fluid films under the washers and seals, and this allows us to lower friction. So Levitas is a seal ring design using that technology, while Levitorg is a thrust washer design. We'll go into that in a little more detail in the next slides. Here's an example of a Levitorg impact of using this technology. There are three examples here. The top example is showing a current design that is in production. We are looking at coefficient of friction on the y-axis, and we're using a Strybeck curve or duty parameter to measure the effects of speeds and pressure. That calculation is listed on the left-hand side. But basically, as you increase speed, you move from the left side to the right side of this graph. As you increase load, you'll move from the right side to the left side. When you're on the far left side, you're at a dry condition where you're not having much lubrication. As you move up in speed, you'll see that lubrication becomes greater and the friction will drop, and you can see that drop in the red line on the current design. If you can optimize friction, you can actually get to a point where you have no contact between the metal, the surfaces of the parts. That's when you go completely fluid dynamic. And you can see that actually in the yellow curve there, an example of one of our patent pending designs where we lower in friction. We reach a low point where we're at the optimum where we're running without parts touching on a fluid film. And then we start to generate an increase in friction as we shear the fluid, and that creates additional friction. But we can optimize using designs to do so. In the example you see here, the yellow product, which is our D4 design, is one design we've used to lower friction and are in production today with that helps these products save energy. And the D7 is a modified version of that design. It's more aggressive in creating fluid shear, so it has a much lower overall profile. But once you generate that shear, you can actually get higher friction because you're shearing so much fluid. So we optimize design based on application conditions and the customer requirements. But again, we're using this technology of using fluid film to generate lift on the parts and reduce friction. And that is critical to really getting to these ultra-low frictions. The estimated CO2 savings on one of these parts was at 0.2 grams per kilometer based on the calculations we used. You can see it can be pretty significant depending on the application and the conditions of use. To move on, I'll talk a little bit about the Levitas seal rings. These are using some of the same technology, but in this case, not a thrust bearing, but a sealing application. Here we have two examples of seals. The first in yellow there is a traditional seal, been used for many years in transmissions. We call a T-shaped seal ring. And you can see the friction coefficient on the graph there is relatively flat as you change during this on the Strybeck curve. You don't get a significant shift in friction as you increase the speeds. The item below that in blue is a new textured seal, this Levitas seal. It has a shape that allows us to use fluid film to promote lowering the friction between the surfaces. And you can see from that one, it's much lower friction. We estimate about 70% lower friction. You can see it's already lower, and you can actually see the Striebeck curve where as it hits a low point, it starts to see fluid shear running completely on a hydrodynamic film. The next slide is an example of how this technology works. So when you look at the graphic here, you can see pressure is allowed to go into this ID geometry on the material, and then is forced up a slope to create a pressure pocket. This pressure then pushes the fluid under the riding surface of the seal, and this way allows us to create this lower friction as you change the RPMs in the condition. We will now play a short video to show you how this actually works.
The fixture on the left contains a Levitas low-friction seal ring. The fixture on the right contains a traditional T-shaped seal ring. As the test begins, each fixture and aero gauge will rotate clockwise, indicating higher torque. The display in the lower right indicates current RPM. As the RPMs increase, there is a reduction in torque within the Levitas seal fixture. This is indicated by the aero gauge moving counterclockwise due to lower friction.
So as you could see on that video, the effect of using fluid to do work to lower friction was observed. We are promoting fluid film under the seal ring, just as we do under the thrust washers, giving us this result of the frictions that you saw. Thank you very much for listening and your time today. I will now hand it over to Lisa for further discussion.
Thank you, Ray. And I want to thank all three of you, Ray, Mike, and Joe. That was an excellent presentation today. It's now time to look at the questions from our webinar audience. Remember, you can send questions to us by putting them in the Ask a Question box on your screen. And our first question is for Mike. And Mike, this question references your slide number 10. So let me bring that up on screen now. And Mike, the question is, what was the name of the part you referenced in slide number 10?
Hey, thanks, Lisa. The name of this part is the diavent. Imagine two words, diaphragm and vent, pushed together, and we called it the diavent.
Very good. Thank you, Mike. And let's see, the next question now goes to Joe. Joe, someone in our audience wants to know about hydrogen-fueled fuel cells. They write, parallel to battery electric, there are efforts going on involving hydrogen-fueled fuel cells. And the question is, are there any current or planned products for the hydrogen storage and fuel cell sealings? Joe?
Well, certainly, thank you, Lisa. Certainly the material advancements are going on right now for sealing the actual hydrogen fuel cells themselves. Of course, these are very sensitive elements with gas diffusion layers and special catalysts that make all the magic happen inside the hydrogen fuel cells. And so, yes, there are special materials that are in use today, and have also in the development for next generation fuel cells that are being designed now to address these sealing concerns, taking into account the very specific chemistries that are used inside these fuel cells.
Very good. Thank you, Joe. I just got a note here. For anyone who wants additional information about the diavent, there is specific information available. So if you want to request that by just sending a new question, submitting a question in the new questions box, you can go ahead and do that. Okay, and now the next question is for Ray. Ray, this question involves PEEK and PPS. This audience member writes, PEEK and PPS are both semi-crystalline. Do you always use semi-crystalline thermoplastics? Ray?
We use a lot of thermoplastic materials that are crystalline because their wear resistance is very high because of the crystalline structure. However, we have tested and evaluated materials that aren't crystalline, like Orum and other materials. Unfortunately, most of those materials tend to increase wear rates. So the semi-crystalline ones have tended to be better in performance overall. Not to say there aren't good performance depending on your cost versus application conditions that you could use.
Okay, thanks, Ray.
Yep.
Joe, this question is for you. Can the flame-resistant material be used for a thermally conductive application?
Surely. Actually, variants of what I talked about today already exist, where we have thermal conductivities, in excess of 1.6 watts per meter Kelvin. And the interesting thing about thermally conductive materials is that many of them actually lose their elastic tendencies at the sacrifice of thermal conductivity. So if you can get a thermally conductive material that has, still some elastic properties, that's really good. These materials are highly elastic and maintain that elasticity through their service life. So yes, it can be used for thermal management.
Thanks, Joe. And Ray, you have this question from our audience. Under fully lubricated conditions, do you see the new material technology influencing the lubricant additive needs? Ray?
We definitely know that one of the critical things for lubricant additives is the effect on these materials. Since these materials are not cheap, they're not your typical nylon, they're pretty resistant. What I would say is when we look at lubrication conditions, we are able to find impacts of some filled systems that work better with additives that we can then lower friction further. Ultimately, most of it's not related to these small amount of additives. It's just generally the system and performance of the application. But there are things we can manipulate in the design of a material to make improvement.
Thanks, Ray. Joe, this is for you. What is the electrical conductivity of the rubber that Freudenberg now offers?
Well, we have a range. Electrical conductivity is a very broad term. So conductivity actually starts at something like volumes as resistivity values at about 10 to the 10th or 10 to the 12th. At those points, those are considered static dissipative materials. When you get down into the really conductive materials, you are 10 and below. So right now, Freudenberg offers materials that are 0.004 ohm centimeters all the way up through the 10 to the 12th, and we have products. For instance, those shaft seals was something on the order of 10 ohm centimeters. So we have a wide range of electrical conductivity.
Thank you, Joe. Mike, this question is for you. In the case where oil is used to directly cool an electric motor, have you looked into how the presence of the lubricant will interact with any of your electrically conducting components with respect to electrical properties or material compatibility? Mike?
Yes, thanks, Lisa. I wanted to pull back up this slide 12 to show the electrically conductive radial shafts that we have with the non-woven rather than the base electrically conductive rubber that Joel was talking about. The way this makes the dynamic connection for the electrical conductivity is from the shaft to the housing, and this is all done on the air side of the seal. So if a wet motor is what I usually refer to it as, but an electric motor that doesn't have, or that is in the presence of oil, you can still put the electrically conductive radial shaft seal on the output shaft seals, and that will contain that electromagnetic interference from getting out of that unit. But generally, with this nonwoven, if if oil gets to that dynamic connection, then it will remove or greatly reduce the conductivity of the component.
Very good. Thanks, Mike. And our next question is for Ray. Can these new low friction and wear seals be used in existing internal combustion engines, vehicles, and drivetrains to improve efficiency and fuel economy of existing vehicles? Ray?
Yes, they absolutely can. So if I move to the slide with the wear and friction performance I showed earlier, the effect of having dry friction the same as lubricated is significant. This material, the Quantix 5514, for example, that we just recently developed, is in testing at a major OEM customer for seal rings to lower the friction in the system, and is being validated today. We're hoping we'll be in production here shortly. They see the benefit in this technology of the material can offer. In addition, we have several customers looking not only at the effect of the material itself, but the design impacts, like the Levitas I mentioned earlier, the low friction seal rings. So that activity in transmission is actually ongoing now, and we have active work with customers.
Thank you, Ray. And Mike, we have another question about the Diavent product offering. Someone wants to know, what material is the Diavent housing made of?
Yes, thanks, Lisa. The Diavent housing is made out of PA, or not commonly known as nylon 6/6 material. And so this is a standard type of product that we've made. If there is something required for a specific customer inquiry, we can look at changing the design to accomplish both of the functions of breathing and emergency release in a unique design for a customer.
Okay, thank you. And Ray, you have this next question. How does Freudenberg wear test results correlate to actual part testing?
Oh, good question. Well, we know that the method we use is aggressive. So when we are testing, we are concerned that really do we see the effects of actual part performance. So we end up actually not only doing the wear standard testing that we've talked about earlier, but we then actually validate parts, and we've seen that we can correlate the wear performance that we see to the actual part performance. But it's important to note it really is about understanding failure modes. So if the condition in the application really runs more towards the dry side versus the lubricated side, that's where we'll have to know, because if we don't understand the application lubrication conditions, we could see an unexpected failure mode because you move from one failure to the next. But we have correlated that. And you can see that actually, I mentioned the slide earlier, but on our slide I'm calling up now, the slide on the pinion gear, this is an example where we validated the actual part performance to the actual wear test method.
Very good. Thank you, Ray. And this question is for Joe. How can the high temperature seals be fabricated?
Well, I showed examples of extruded shapes there, but the high temperature seals also lend themselves to all forms of rubber fabrication. Now that can be injection molding, whether it's conventional hot runner or open runner or valve gated cold runner. It can be wasteless transfer molded. It can be conventional transfer molded. It of course can be compression molded. Can be autoclave cured, can be conventional thermal exposed cure in a pressured mold. So it'll really allow itself for all methods of rubber fabrication.
Very good. Thanks, Joe. And Ray, this question is for you. What effects do changes in fluid viscosity have on the performance of Levitorg thrust washers?
Oh, that's another good question. When you change fluid viscosity, like many of the new fluids that we're going to improve efficiency, you actually change the amount of fluid film you can generate. So when we create one of these Striebeck curves, example in the Levitorg slide I'm calling up now, you can see that friction is lowering as we change speed. But in effect, what you're doing is by changing the viscosity of the fluid, you're shifting the curve. So lower viscosity fluids would run much lower film thicknesses and would actually run drier, making the curve move to the left-hand side. So you have to then try to compensate, because if I have a rough surface, I have to have a fluid film thickness large enough to overcome the contacts of those roughnesses. So very significant impacts.
Very good, Ray. Thank you. And here's another question for you, Ray. Do you see any impact on fatigue resistance with the new PEEK versus FC30 PEEK?
FC30 is a material that's been around a long time. It's a very good material overall. The issue, I would say, is it's not been designed for dry running conditions. So when I call up that data in this graph, you can see the FC30 there. From a fatigue standpoint, it's actually pretty beneficial. If I'm concentrating on a fatigue failure, then I would make sure the filled system has the proper materials for it. So for example, if you look at the green material there, that's not a fatigue resistant material. It's not been designed for that. Its failure would be quicker than the FC130. But when you compare that to the 5514, that example is a material that's much more fatigue tolerant. Those are different failure modes that are tested for in different ways. So not shown in a wear and friction test here.
Very good. Thank you, Ray. And with that, I'm afraid we're out of time, and that's all the questions we can get to. But I want to thank our speakers, Ray, Mike, and Joe, for just a wonderful discussion today. I also want to thank our audience for being with us. A survey will pop up on everyone's screen in a few moments. Please tell us what you thought of our program by answering 3 short questions. This webinar will be available on the SAE website. An email will be sent to everyone who registered for it as soon as the archive is ready. And I'm Lisa Rigo with SA International. Thanks for joining us.